Hello guys, that is the analysis of the indeterminate structure. Here we have the frame that has the fixed moment, fixed support here, and the other fixed support here, and we have a pinned support here, and UDL of 65 kilonewton meter. We have 3 distance, and distance between the two fixed end support is 3 plus 3 is equal to 6. But we are here to analyze this equation by using the moment distribution method to determine the end moments at the support of the frame in this figure, AI when is constant. We start to find the fixed end moment fixed end moment AB is equal to 0 kilonewton meter, because of here from point A up to point B there is no any force acting on that frame. That's why we analyze the fixed end moment as 0 kilonewton meter. Then fixed end moment BA again is 0 kilonewton meter. We remember that in the condition of equilibrium, the fixed end moment here we have accordingly to B up to A and A up to B must be equally accordingly, because the distance is the same. That here have a 0 kilonewton. Then fixed end moment BC must be equal to 0 kilonewton meter. Then it's the same as here. Then fixed end moment CB usually is equal to 0 kilonewton meter. But here the fixed end moment BD is equal to WR square over 12 with the negative, because of we count anti-clockwise direction with the moment. We will have the 65 factor of 3 square over 12 with the negative must be equal to, here we must have the 65 times 9 over 12, 65 times 9 over 12, we must have 48.75 is the negative kilonewton meter. Then fixed end moment from point D up to B is equal to WR square over 12. Is the same as this but different in the sign. We have 48.75 kilonewton meter. Then here, when we analyze the frame by using moments distribution, we apply or analyze distribution factor. Distribution factor as DF is equal to member stiffness over summation of member stiffness. Here, member of stiffness must be equal to the I over R. But here we start to analyze the member stiffness of every span. Here we have the distribution factor AB must be equal to what? But here distribution factor AB must be equal to member stiffness AB over summation of member stiffness. But here we focus about when we have different of support. When we have a fixed support, distribution factor must be equal to 0. When we have a roller or hinge at the end, of beam or frame, the distribution factor must be equal to 1. But here the distribution factor AB, because of for AB we have this fixed support, the distribution factor must be equal to 0. Then and distribution factor CB must be equal to 0. Distribution factor CB must be equal to 0. But here we started to compute stiffness BA must be equal to I over 3. We have a 0.33 I. Then distribution factor BC even and the member stiffness at BC is the same as the del 0.33 I. Then member stiffness at BD is equal to 3 over 4 times I over 3 must be equal to 3 over 4 times 0.3. We have 0.247. Around we have 0.25. Have 0.25. BD must be equal to 0.25. After we get this, we start our, then here distribution factor at dB must be equal to 1, because of is the roller support here. Distribution factor must be equal to 1. Then here we continue to analyze the distribution factor. Distribution factor BA must be equal to 0.33 as member stiffness over 0.33, then plus 0.33, then plus 0.25. We obtain that by using 0.33 over 0.1 have 0.36 as distribution factor of BA. Distribution factor of BC is the same as this, is equal to 0.36. Then distribution factor BD is equal to 0.25 over 0.33 plus 0.33, then plus 0.25. We have seen the .25 over 0.91, we have 0.27 as a distribution factor of BD. After we get that, we start to calculate an balanced moment analysis. Here you have the distribution factor AB. We must have the distribution factor AB is equal to 0. Take a 0 here. And distribution factor BC, BA, distribution factor BA, we have this distribution factor BA, we have a 0.36, distribution factor BA, distribution factor AB. Then another is distribution factor BD. Distribution factor BD is equal to 0.27. Then you have distribution factor BC as 0.36. We have other as distribution factor. We have this distribution factor AB and BA, distribution factor BD, have distribution factor BC, distribution factor CB is equal to 0, like this. Another is distribution factor BB is equal to 1, as this one. Then fixed end moment here is equal to 0 as this, and BA is equal to 0. Then BC is equal to 0. CB is equal to 0. But here we have negative 48.75 and here 48.75 kilonewton meter. Here we analyze by take this and multiply this, we get 0. Then here we get 48 as summation of this. Then multiply by distribution factor with the negative sign. Negative and negative get positive. 0.36 multiply 48.75, we get 17.55, and here is equal to 17.55 because it's the sign. Then we have 48.75 times 0.27, we get 13.16, and it's tetra. Then here 0 times 0 is equal to 0. Then here 48 times negative 1 is equal to negative 48.75. That is the first law of Calver-Olls-CO. Then we take this, then make close with divide by 2. Take this, then divide by 2. Here we have the 0, and here we take this 13.16, then divide by 2, then we pass here, and this we divide by 2. We take the 17.55 over 2, we get 8.775. Then here BC must flow this is 8.775 with the cross, and this and this, we take the 13.16 over 2, we get 6.58. Then here BC, then we take a 0, and here, then here we get negative 48.75 over 2, we get here as negative 24.375. After we get that, we multiply this to the dissolution factor, where we must have this and times this is equal to 0, and this is equal to 24 as total, then times 0.36 times 0.36, we have here 8.755, because it is negative and we multiply add this negative, we get the positive, and here is equal to 8.75. Then after that, this we multiply to this, multiply 2.27, you get 6.58 as positive, and this by multiply to 0 we get 0, and this to multiply to negative 1 is equal to negative 6.58. That is the second law. But here we must see to add in order to compute an balanced member. By now here, when we want to analyze that by using an balanced moment, we must add this part and this part, and even this part we add, then all total is different moment AB, moment BA, moment BD, moment BC, moment CB, and even and moment DB here. But to continue with the unbalanced moment, when we stop here, we must have the total. Here the total is 8.775. By now here is got to 8.775, then plus 17.55, you get here 26.35. By then here we add by take off 48.75 negative, then plus 13.16, then negative 24.375, then plus 6.58 is equal to negative 53.38. Then here is the same as here, is equal to 26.35. And now here is equal to 8.775, and this here is equal to 0. But now we remember that the question is to determine the end moment at the support. But now end moment at support, moment AB is equal to this one, 8.775 kilonewton meter. The moment BA is equal to 26.35 kilonewton meter. Then moment BC is equal to 26.35 kilonewton meter. Moment CB is equal to 8.775 kilonewton meter. Moment BD is equal to negative 53.38 kilonewton meter. Then moment dB is equal to 0 kilonewton meter. By using different direction, and that we have this as the final end moment of that the frame structure. That is the end of this equation. Thank you for your watching this video. Continue to be blessed.